Hello, today we're going to be looking at the next periodic trend, which is ionisation energy. Today we're going to focus on first ionisation energy. We're going to start with a starter, a wee activity for you to do. So if you pause your videos now to work through the questions here. Now the first, an ion electron equation for sodium losing an electron. I want to first of all start with this one by showing what it's not. A very common mistake that people make because they're so used to doing maths and having equations where you add stuff and take them away. When you're asked to write an equation for sodium losing an electron, what they'll start writing is sodium minus an electron, giving you sodium positive. Now, that is not the case, that's not correct, because an equation in chemistry, it shows us like a before and an after picture. So here, this is what you're starting with, and this is what you're finishing with. You can't have a taking away of an electron, it just doesn't make sense. So the way we write it, like I said, it's a before and after picture. We're starting with sodium, we're ending up with a sodium ion, and we say, well, it's a full atom that we're starting with, it's an ion that we're ending up with, and an electron. So that's showing the ion electron equation for a sodium atom losing an electron, starting with the sodium atom, ending up with your ion and your detached electron. Okay, our second one, a copper 1 positive ion losing an electron to form copper 2 positive ion. Same idea, we want a before and an after. We're starting with Cu1 positive, we're ending up with Cu2 positive, and the electron that we just pulled off. And our third problem, Fe2 positive losing an electron to form Fe3 positive. Before and after, we're starting with Fe2 positive, we're pulling off an electron to become Fe3 positive, so Fe3 positive and the electron. We're talking about first ionisation energy, and what that is, it's a measure of how tightly something holds onto its electrons, or looking at it another way, it's the amount of energy involved in removing electrons from an atom. So if we go back to this equation, that was our first question in the starter activity. This is taking sodium and removing an electron to make a sodium ion. So it's the energy associated with this change. But you'll find in the data booklet on page 11 a whole set of values. We're just going to be interested in the first ionisation energy for these elements just now. And we want to be quite clear on something. We've got to compare like with like. So all these values are taken from a starting point of the elements being in the gas phase. So we're starting with elements in the gas phase, we're turning them into ions which are still in the gas phase. Next wee thing we just need to be clear on before we get stuck in, it is always 1 mole, and if you look at the top of the chart, it's got the heading ionisation energy in kilojoules per mole. It's the amount of energy to remove 1 mole of electrons. So we're starting off with 1 mole of atoms in the gas phase and removing 1 mole of electrons. We've recently understood that when we're talking about 1 mole, it's just talking about a very big number, 602 hexillion. So you're starting with a mole of that, you're removing a mole of electrons till you leave you a mole of the 1 positive ions. So on my wee chalkboard, we've got a wee definition. Now you see it written slightly different ways in different places. The crucial thing is it's talking about the energy to remove 1 mole of electrons from 1 mole of atoms, and crucially in the gas phase. Actually, I'd highlight atoms as well. It's quite important. We're talking about 1 mole of atoms. So we're going to have a start having a wee look at the figures on page 11 and see what trends there are, and then have a look at trying to sort of account for those trends. So we first of all, if we look down our first period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. We've got values starting at 520, increasing to 900, slight dip, 801 for boron, but carry on our upward trend of 1086 and so on. Slight dip again for oxygen, but up again for fluorine and neon. So on the whole, these values are increasing. Along the second period rather, the values are increasing. For our second set there, the third period, going sodium, magnesium, aluminium, you're seeing a similar sort of idea, a general upward trend with one or two wee blips, one or two wee exceptions. We've got a slightly lower than expected value perhaps for aluminium, first ionization energy of aluminium, and a slightly lower than expected value for sulfur. In advanced higher next year, we can actually get our heads around where these wee dips are coming from. So in general though, along a period, you see an increase in the amount of energy it requires to remove 1 mole of electrons from 1 mole of gaseous atoms. If we look back to a previous trend, we saw atoms getting smaller, the atomic size decreasing along a period. And why was that? There was an increasing nuclear charge as you went along, more and more protons in the nucleus. And that's the same reason behind this increase in first ionization energy along a period. Because in each successive element, you've got extra protons in the nucleus pulling those outer electrons tightly. So the amount of energy that you need to remove an electron is going to get bigger as you go along. And there's a second wee point here, which is the outer electron is getting closer and closer and closer to the nucleus. So you're feeling an extra pull there. So there's really two factors that we would use to account for this increase in first ionization energy. First of all, there's an increasing nuclear charge as you go along a period, and secondly, the electron that you're trying to remove is closer to the nucleus. So we want to also look at the trend down a group. So if we picked out the alkali metals for a start, lithium, sodium, potassium, rubidium, cesium, and look at the values for the first ionization energy. Lithium 520, sodium a bit lower 496, potassium a bit lower 419, rubidium lower again 403, cesium 376. So we're seeing a steady-ish decrease in first ionization energy down in the alkali metals. So how do we account for this change? Going down a group, you see a decrease in the first ionization energy. Well, if you look at lithium first of all, we saw the other day, that's quite a small atom. Sodium is a bit bigger, there's an extra shell of electrons. Potassium a bit bigger still, rubidium even bigger still. And this actually leads us into our understanding of why we're getting a decrease in first ionization energy going down a group. Why we need less energy to remove an electron. So a couple of wee points. First of all, the outer electron that you're removing is further away from the nucleus, isn't it? As you go down, they're getting bigger and bigger. You're not going to get that full force of the attraction as if it was really, really, really close. There's a second point though, that's perhaps more obvious when you think about it. If you imagine this particular electron versus this electron, removing these two electrons, lithium is going to be feeling the force of the nucleus, rubidium is going to be feeling the force of the nucleus, but the difference here is there's lots and lots and lots of electrons in between that electron and the nucleus. It's almost like they're kind of buffering that electron from the full sort of nuclear force of attraction. So it's a bit dampened down, and there's two words that we use to describe that. We describe that electron as being shielded or screened from the nuclear force. So, recapping then, going down a group, there are two factors to account for the decrease in first ionization energy. You've got a further distance from the nucleus as you go down, and also you get screening or shielding from the inner electrons, which both reduce the amount of energy required to remove that electron. Okay, and so to conclude, we want a nice clear definition of what first ionization energy is, and we want to be able to account for what the two trends are along the periodic table. So first of all, our nice clear definition. First ionization energy is the energy that's required to remove 1 mole of electrons from 1 mole of atoms in the gas phase. Secondly, what were the two trends? First of all, along a period, the values got larger and larger and larger. So along a period, the first ionization energy increases. Why was that? We said, well, there's two things to account for that. First of all, you've got an increasing nuclear charge, and also that electron that you're trying to remove is held closer to the nucleus because the atoms are smaller. Secondly, going down a group, what was the trend? The trend was that the values got lower and lower and lower. Okay, first ionization decreases down a group. And how did we account for that? We said, well, removing that electron, as you go down a group, and it works for any group, as you go down a group, that electron that you're trying to remove is further from the nucleus just because the atoms are bigger. But there was a second effect though, which is that these bigger atoms have got a lot more electrons between the outer electron and the nucleus, so that they get shielded or screened from that full nuclear force.